challenging. That's why I didn't take an action.
So if you look at your number 32, the first problem, I think 17, gave you z equals something, so that should have just been using substitution, plugging one into the previous, those two into the previous. 21 had one solution, 27 did not have a solution, so you should not have gotten a solution for 27. 31 and 32 were the infinitely many solutions. So if you got no solution for one of them, or if you found a solution for one of them, then you went wrong somewhere. So looking at number 32, since this is the even one, the answer isn't in the back of the book. I figured we'd go through this. When you're using Gaussian elimination, the goal is to eliminate variables from the problem so that you eventually can solve for one of them. I usually eliminate alphabetically, so I eliminate x first, and I do the same thing every time, just to stay consistent, systematic, because once you get 5, if you can keep the same system, it really does work easier for you, even though it's going to be more work. So if we're looking at the second equation, and we have a 4x in the second equation.
I do.
There you go. Using the first equation and comparing it to the second, Anna, what could you multiply the first equation by so that we eliminate the 4x in the second equation?
I multiply the first equation by -4.
Yeah. So taking the first equation, multiplying it by -4, and then that gives you what, Anna?
-4x minus 16z is -52.
Okay, nice. So again, the goal is to eliminate the x's. So underneath it, we're trying to get rid of that 4x for the first case here. And when we combine them together, our x's are now gone. And Anna, you end up with? And
I got -2y and then -15z equals -45.
yeah, I should have spaced mine out a little better. So here are the z terms. There is not a y term to combine with. So that would be our first resulting equation. The solution that we got from combining 1 and 2 together. We've eliminated the x in the second equation. So now if you go back and try it again, now we're going to try to get the x in the third equation out. Because once you choose one variable, you want to eliminate both of them from the problem. So, Zach Streza, what could I multiply equation 1 by to eliminate the 2x in the third equation?
Multiply by -2.
So we can multiply it by -2, and then that gives us?
-2x minus 8z equals -26.
Yeah, lining those up a little better there. So when you combine those, Zach, what do you get?
The x will cancel.
Yep.
You'll get -2y minus 15z equals, that's going to be negative, I said -45.
Yeah, that's -45, that's right. So -2y minus 15z equals -45. If they're all the same, when you subtract the second equation, you end up with 0 equals 0. If the left side has the same numbers, but the right side values are different, that's when you're going to have no solution. So if the first one was a 45 and the second one was a 47, then we would have no solution. But we have infinitely many solutions because they all cancel. Because with elimination, you're taking one and subtracting the second one from it. Or if they have opposite signs, you're adding them together. Well, here they have different signs, or the same signs, so we can subtract the second and they become opposites. So once you know there's infinitely many solutions, you can't stop there. Because you can't just pick 3 random values and assume it's going to work. The 3 random values actually have a pattern, so they're not quite so random. And you can choose any of the variables to try and solve for. So you could take this equation here that has 2 letters in it and get y by itself. You could take the first equation here that also has 2 letters in it and try and get x by itself. But we need to be able to get one of those variables by itself. Okay.
I started with z.
Yeah, so she said z equals a. So if we let z equals a, and that's generally how I start, because with Gaussian elimination, you eliminate the variables in order, and the goal is really to get a z by itself first. So if we let z equals a, based off of that first equation, it says x plus 4z, well z is now a, is equal to 13. So now we're trying to describe or define the way to find the other values. So Katie, in this case, x would be equal to
Negative 4a plus 13.
-4a plus 13. So now we have x written as a pattern with a, and we have z. So again, if you stay consistent and always start with z, let z equals a every single time. It's the last variable that you'll try to eliminate, but it's really that first variable that we're solving for. And then now that we know z is equal to a and x is equal to -4a plus 13, we just need y yet. And here's an equation involving y. Here's an equation involving y. They're the same. So you pick one of them that has a y in it and a z, and you replace the z with a. So we have -2y minus 15 times a equals -45. So again, the goal is to get 3 variables to have the same pattern or term in them, so that there is a pattern that we can use to find the values. So if we take the 15 to the other side, we end up with 15a plus 45, and then when you divide by -2, hopefully I have more space over there.
Miss Kay,
Yes,
would it be 15 minus 45 because
Yeah. I think I said minus. I just don't think I wrote. Did I say plus? Okay. So my y term, when I divide by -2, the negative really can't stay in the denominator of a fraction, so it goes to the numerator. And we get -15a plus 45, and then divided by +2. So here's my y. So now I've solved for x, y, and z, but they all have that same constant value in them, that a term. So when you write your order triple, a was -14 plus 13, and then we have -15a.
it's negative 4 plus 2.
What is my problem?
I forgot to do this.
Thanks. Plus 45, and then finally z is just a. No, because you were dividing by -2, so dividing by -2 is not obvious.
So if you had like a number for z and it wasn't like infinite many solutions, could you plug that z into like any of the equations, even like
Yes.
the ones you made?
Yes. Yes.
And we're gonna-
So the goal would be then, if I said find 3 solutions to this system, you would start with z and say if I made z equals 2, then I could find the other values. So I should be able to still come up with answers, as many answers as we wanted. We all come up with our own answer by starting with the value of z. So if z was 2, then I could plug a 2 in here and get -8 plus 13, so my a would be 5. We could plug a 2 in here, so we would have 5 something and 2. So that would give us -30, 15 halves. So that would be an ordered triple that could work based off of the pattern of each term. Questions? But you can't just stop at 0 equals 0, because that doesn't really tell us anything about the answer. Besides there, yes, infinitely many solutions, but because there's 3 terms and no longer 2, it really has to be a specific way that those values are created. Questions? So in your notes, we're going to do another one that is similar to this. So the answer is going to have that like pattern that we're going to try and create, and those are going to be the ones that are a little trickier to try and see if you can start with the z term and work your way backwards. So yesterday we did one system that worked out nicely and had an ordered triple, one that had no solution, and then the one that had infinitely many. And then we also solved one with matrices, kind of reviewing how to plug the information into the matrices. The other type of system that exists is a system that's called a non-square system. And it says a system of equations which the number of equations is not equal to the number of variables is called a non-square system. So usually if we have 3 variables, you have 3 equations to solve for. If you have 4 variables, you'll have 4 equations to solve for. if there are not enough equations compared to the number of variables, then there can't be a unique solution. What's a unique solution? So why would a solution be called a unique solution?
Because it's one solution.
Because it's one solution. So a unique solution is just finding one answer, like 2, 3, 4. That's the solution to my system. It's unique because there's one location where all three of our planes are intersecting with each other. Or all three of the variables are intersecting with each other. So if I don't have 3 equations, there's no way that we can use elimination to eliminate 2 of the 3 variables from the 3 equations. So we can still solve it and get a pattern for the solution, but that pattern will never have one answer. It's going to have infinite. So every non-square system will have infinite solutions. So we're still going to try and work through it the same process, the same method. I have 2 equations. The goal would be to get rid of the x in the second equation. So we'll always try and just eliminate the first variable in the alphabet. So Nina, what could I multiply the top equation by to eliminate the x in the second equation? -2. And again, like you could say, hey, but I'd rather eliminate z. Fine, eliminate z. I just like working alphabetically and getting rid of the letters in order. But that's just me being OCD. So it's okay if you see something else, because there are multiple ways to solve. Nina, if you multiply the first equation by -2, what do you get?
-2x plus 4y minus 2z equals.
And then when you combine them together, x's cancel.
And then 3y minus 3z.
-4, you were right.
I couldn't tell if that was
No, that's fine. I tried to squeeze it. So we get 3y minus 3z equals -3. What do you think you could do with all 3 of those values? Take a 3 out. I mean, they're all divisible by 3. So you can take a 3 out. Y minus z equals -1. As long as you do every single piece, you can do that. So if they're all divisible by 3, you're allowed to divide everything by 3.
What happened to the 3 though?
Well, because I divided it on both sides.
Do we have to put it anywhere?
No, it's gone.
No.
No,
So it's not lit.
it's not in there. You didn't factor it out. Literally, if you divide it from the left and the right, the 3 is gone. Because you've taken it out of both sides of the equation. It's a magic trick. It's gone. So this resulting equation is as far as you can go with solving the problem. Because there is not a third equation that we can use to get another piece of it to try and continue to break it down. So like you can't go any further solving. This is it. But we can try and at least start to say, okay, well, I like having issues right. I don't know why. This is a minus. I cannot write it. Okay. So we can now say, we can't solve anymore with elimination, but we can take that step where we start to try and write or formalize an answer. Oh. So we're going to say let z equal a. So then if you go to the equation that just has the y and z, because at least we eliminated the x from it, we can then find y by taking y minus a equals -1. So at least we can try and have an expression that has the same constant term in it, a, in every piece. So y would be equal to a minus 1. So z is equal to a, y is a minus 1. How could we find x?
plug in the other.
Yeah, plug it into the other equation.
Oh, I got some T's.
That's a what?
T.
Ooh. Interesting solution.
A very interesting solution.
A very interesting solution.
Dave and I have the T.
I got the T. Nope, I don't. Yeah, I do.
Okay, isn't z a, so couldn't you put it a?
I'm gonna quit. I'm done. Done for the day. I'm not really sure. minus 2a plus 2 plus a equals 2. So x is equal to
A.
a.
That's the T.
Yeah,
Okay, that's the
that's t.
Oh, I see what I did.
So when you write your order triple, a and a for x and z tells us that x and z have to be the same. And y is 1 less than it. So you could have 3, 2, 3. You could have 5, 4, 5. You could have negative 1, negative 2, negative 1. Questions? So when it's a non-square system, there really is less work because you're using elimination once because there isn't another equation that you can eliminate from. But you need to make sure that you still write the answer with that pattern. Ethan, question or you're just... Okay, good. Alright. Alright, so if you flip the page, we're going to do one other problem today. And this is an application problem, but it does say you can use matrices if you want to solve, or you can use Gaussian elimination if you want to solve. It's totally your choice for this one. So because it's an application, requires a little bit extra thinking, we'll go easy with the solving part. Find a quadratic equation of the form y equals ax squared plus bx plus c. That's that general form of a quadratic, pretty much the way that we factor almost all of the problems that we factor. We want to find that equation so that it passes through the points negative 1, 3, 1, 1, 2, 6. And it does say you can use matrices to solve the system. So it is going to be a system. So our goal is to try and create a system from that information. Ethan, what do you think? Plug in the x's and y's. So if you have a point and it's on a graph, that point represents an x on your graph and a y on the graph. Well, that equation, y equals ax squared plus bx plus c, has x's and y's in them as well. So he said plug them in. So I'm taking the ordered pair negative 1 and 3, plugging it in for x and y, but not a, because we don't know a. A is the coefficient that goes in front of the x squared. We don't have that number yet. But we can plug in the x term. So if I simplify this a little bit, we would have 3 equals a minus b plus c. 1 squared, negative 1 squared is still 1, but it's now a negative b and a c. So Ethan, what do you think you would do next? Yeah, do it for the others. So you have 3 ordered pairs. If I'm going to have a system of equations with 3 variables, a, b, and c, I probably should have 3 equations to go along with them. So take the second point and plug it in for x and y. So that now says 1 equals a plus b plus c. And then same thing with the third point. So our last equation would say 6 equals 4a plus 2b plus c. Questions? So if you want to use Gaussian elimination, feel free to do so. And if it makes you feel better that the equal sign is on the right side, you can flip it and put it equal to 3, equal to 1, and equal to 6. Totally up to you. But it does say you're allowed to use matrices, and there are 3 problems that is listed on your assignment sheet that says you can use matrices for those 3 problems. Do so if you want to. Don't if you don't want to use matrices. Totally up to you. But like if it says you can use the matrices, you might as well use them. But if you're plugging it into a matrix, I need to see the information that you're plugging into the calculator. So the first matrix would be the coefficients for the first equation on the row here. So we have 1, negative 1, and 1. So the first row is equation 1. The second row would be equation 2's coefficients, and then the third row, the 4, the 2, and the 1. So remember, that's matrix A, and we're taking the inverse of matrix A. So you're going to take the inverse of matrix A and multiply it by that 3, 1, and 6. So So if you'd like to use a matrix, you can use the matrix.
Even on
Even on the homework, there's 3 that you can use it.
the
So I think there are 4 problems that say do algebraically. There are 3 problems on the homework that say you can use matrices. So feel free to use the matrix if you'd like to solve it that way. So remember when you're plugging it into the calculator using second x negative 1, plugging the numbers in for A, second x negative 1, going over, plugging the numbers in for B.
This is so exciting.
Anybody have an answer? Emily? Or Katie?
2 negative 1.
Zach, did you get the same answer?
I did.
How would you write that answer? So like make sure you're answering the question. What did the question say?
Oh. Would it be your A, B, and C?
Yeah, that's your A, B, and C. So make sure that you're answering the question because we're not finding an intersection point. I mean, yes, that is the intersection point, but we're finding the values that are the coefficients for our equation. So A is 2, B is negative 1, C is 0, so the equation would be 2x squared minus x. So just make sure that you're answering what the question is asking you. Question. So tomorrow we'll do that final word problem. There is a word problem, it's the last one of your homework. So look at it, see if you can create a system of equations. You're going to need 3 equations now instead of 2. We'll talk about the word problem tomorrow for sure.
Didn't you already do this, Katie? That's like one of the homework.
So you're doing it now using matrices. Yep.
Oh, okay.
Yes, please.
I'm sorry that I wasn't here. I get to go to I actually like it.
Oh, good.
I think they're
I'm
fun.
gonna go to
Yeah.
And then Katie, you
Yeah.
missed a factoring quiz at the beginning of class.
Okay.
Do you think you should come by tomorrow morning?
Yes, I'm still gonna what?
That's all right.
Is the homework in the book
Yeah, I'll be
tonight?
there tomorrow morning.
Yeah.
Yes, it's in the book tonight.
Okay.
Welcome to
I'll just come down.
Thank you.
It's all on the same page.
I'm coming from your husband,
Oh, for real?
so he won't require.
Okay. David, question?
I was just gonna come take a picture of the book. Did you hang this in your room?
I can.
Thanks.
It's like all fancy.
Emily, you're
Yeah.
a mistake, Cobra.
We're the ones working on last night.
Oh, that's right. It's not really called Saint Sebastian.
Yeah, they checked because they grouped all the
Yeah.
sections and everything.
Everybody has their name.
Right. Simon is
$4.99.
You're having an issue. $4.99.
I always have.
I might have
Right, very slow.
pages less than I might have it.
Yeah.
I wanted to
But you're gonna need this
Oh.
So you need these 2. I don't know. Probably
I did.
and this page.
This has nothing to do with math or anything,
Well,
but
that's
a couple days ago I got an invite, well, kind of like an invite to attend this 6-day long cooking class thing in New York over the
Oh,
summer.
wow. Cooking.
Yeah.
That's cool.
Yeah.
Very cool.
I'm excited.
Do you I guess you like to cook, parents?
I did more when I was homeschooled and actually had time,
Okay.
but
No time now.
See you, Miss Katie.
See you, David. Jared, you know you're supposed to leave and go to your next class, right?
Yeah.
Okay. Okay. Although I'm sure Hare will love for you to stay too.
I don't think you will.